And now let's move on to the acceleration. And as you know, because graphite is rotation, so there are two types of the acceleration. The first two components, the first components of acceleration that we call is tangential. So let's talk about the acceleration. And the first components is the tangential components of the acceleration. So if you recall, to find out the tangential components of acceleration, we take the derivative, first derivative of the velocity. So at, tangential components of acceleration, equal to first derivative of velocity over dt. And recall, we have equation is v equal to omega r. So let me replace that in here. It equal to d over dt omega r. And when we have that here, d over dt omega r, so if you talking about the math, we can have it d omega over dt times the radius, right? And we plus the omega time d times d radius over dt. But as you can see, the richest body, so the radius, what is radius? Radius is from the fixed point A to any point that we study, in this case for the acceleration, point B, then AB, richest body, regardless of how you change, we assume it reaches, so that radius remain unchanged over time. So the derivative, it should be equal to 0. So from that, we can have this one equal to 0. So when that one goes 0, because as you can see, r is always constant for the richest body. So from that, we can rewrite at tangential components is equal to d omega over dt r. And if we set d omega over dt, and as you can see, the omega, what is omega? Omega equals to d theta over dt, and then it also equal to the second derivative of the rotational angle. And let me set that equal to alpha, and let me box this equation here, very important. Alpha, basically the first derivative of the angular velocity, and then the second derivative with regard to time of the rotational angles. So this one, we call that is a angular acceleration. So that concept is angular acceleration. We have velocity, we have angular velocity. Acceleration, we have angular acceleration. So with that angular acceleration, we can have the unit of this one, and you can see unit of the angular acceleration are radians, because it's angle second square. And that unit for the omega is radian per second. So velocity, angular velocity for angular acceleration, radian per second. So keep that in mind. And then we can write the two equations for this time of motion. So the two time of motion for this one is, two equation for the tangential components of acceleration. It distracted a little bit when my kids jumping outside. So let's write down here at equal to alpha body time radius of B relative to A. So that will be scalar. As you recall, for the velocity, we have the same scalar equation. And then, if we're talking about the acceleration, we have for the vector tangential components, it will be alpha, for example, point B, right? Then we can have alpha. Let's change a little bit here. So point B tangential components. So make it simpler for our simple tangential component for the point B. It will be equal to alpha body vector cross with the position vector to be from A, and this will be a vector form. Sense? And this again, it only apply for Rafa motion. What is for GPM? We talk next time, next week. Rafa, next lesson, by the way. Rafa only, and that the same right here. It also, this equation apply for Rafa only. For the acceleration, also apply for Rafa only. In terms of the characteristics of the acceleration, and in this case tangential components, we have AT also perpendicular to the radius and consistent with alpha. Consistent with the angular acceleration. So same as velocity perpendicular to the radius and consistent with omega. So let me show it in the Rafa stick back here before we continue. What is AT? So if we have a point B in here, then we have the Rafa stick for acceleration. If we add in the one component for tangential components of acceleration, let me assume this Rafa body deceleration. So it means decreasing speed. So the alpha, it will be opposite of the omega. So if omega in this case clockwise, alpha counterclockwise when the body deceleration or decreasing speed. So then at that point we can have the tangential components A BT. It will be perpendicular to the radius and consistent with alpha, which is go to the left. So as you can see, keep that in mind. Alpha and omega can be not the same direction. It can be opposite direction if the body in fact deceleration. And then let's move on to the next components with the normal components. Acceleration, normal. For acceleration normal, if you recall for the equation for the acceleration in normal components, so we have it an it equal to v square over rho, when rho is the radius of curvature. And from the previous equation, we have v equal to omega r, so omega r square over radius. If Rafa stick, it will be rho become the radius. And with that, we can have that is omega square r. We simplify this ratio, we have omega square r. So from that, we can have the two equation for normal acceleration. So A AB for normal components, it will be equal to omega of the body, because when we talk about omega, we talk about that body, square radius B relative to A, or from A to B. Okay, and then and same at alpha here, we talk about the alpha here body properties. And when we have the vector form, then I have A, B, and vector. It will be equal to cross product, so omega body, any point on that body have the same, and then cross with omega square, so it break down omega body cross with the radius, the position vector to be from A. And again, these two equations will apply for Rafa only. Rafa only. Keep that in mind. And with that, what is the direction for AN? And we already learned that in practical kinematic. AN will be parallel to the radius. Parallel to the radius. And point to the fixed axis. Just like in practical, it will be direct to the center of the rotation. So point or direct to fixed axis. Okay, so let me show that point that in here. What do we mean when it point to the fixed axis? Go to the Rafa stick. So let's talk about the normal acceleration. Will be someone call, just like in class, everyone sometimes call, but you don't pick the phone. But the problem is to show it in here. So here we have A, B, N. So as you can see, it will be parallel to the radius at that location and point to the fixed axis, point A over there. So that is A, B, N. Normal components. So let me make a few notes before we conclude for this video, before we move on to another short video for the class. So let's continue. Here we have A, T, and AN. We need to specify which point. So this is a point property. And then the alpha, like omega, it will be a body properties. Property. Body property. So any point on the body will have the same body properties. Any point on the body have different point properties. Keep that in mind. So the total angles for this, it will be alpha A, the total acceleration of a point include 2. So we have an alpha cross R. For the tangential components, you see basically tangential components plus the normal components, which is omega cross position vector, and this is the normal component, and these two components are perpendicular together. And I will the YouTube link for the first video I also posted for the note in there. So with that, let's stop here for this video. Next video, it will be very short about the emphasize the importance of point and body properties.